Good afternoon, students. Welcome to our physics webinar class. Here we are discussing concept-related concepts on wave optics, right? So the other day we are incorporate the new concept that we're discussing, that Young's double slit experiment. Okay, so Young's double slit experiment. So here we are using the light. We are using the light. This slit force So this second means the first slit acts as a the second slit acts as a the source over here, and next to that we are using double slit. See, for this double slit, what happened? For these two holes are there, and from these two, again at a time, two waves are coming out of this source. So A and B sources of the secondary source. This is first source, this is the secondary source. And from these two, the A and B, the waves are coming out. And we know the waves as crests and troughs, right? See, observe this diagram. The thick lines, all the thick lines are crests, and the gap between any two, observe this, for example, A here, this is one wave, this is another wave, this one is next wave, right? And this one is third wave, like so. And the gaps between them means the blanks between the two waves is trough. So observe on the yellow line case, two troughs are intersected here. Two troughs of the two waves are intersected, and that will be appear on the screen. This is the screen here, on the screen as a maximum. And observe this one trough and other crust are overlapping, this point, this point, this point. So those are called minimum points. So maximum, minimum. So on the screen, you can see the alternate bright and dark fringes, So this is called interference pattern. So this is due to what? Interference of two waves. What is interference? Superimposition of two waves, or okay, that is called superimposition. When the pattern, if you want to see on the screen, that will be like this, alternate bright and dark fringes. And for them, we can calculate the fringe width means gap between either too bright or too dull, means dark fringes we can calculate. So here on the screen, randomly look at this diagram, randomly at a particular point P. Okay, this is actually is the the picture of Young's double slit experiment over here, right? So for this, look at this. This is the source. This is the gap between the two slits here. That is S1 and S2 are here. Okay, the gap between them is small d is given over there. And now let us take one ray from S1 is moving over here, and S2 means on the screen randomly we are picking one point that we need to calculate whether that point is bright or dark, that is maximum or min, right? So here is the two waves are intersected at a particular point. Now, so look at this at a point P, okay, is at a distance y on the screen from the O to P. From O to P, the distance is, let us take y here, right? And the screen is kept exactly at what distance is given capital D. Capital D is the distance between the slit and the screen. Slit and the screen, right? So all the dimensions we have now, that is small d is the gap between the two slits, capital D is the distance between the slit and the screen, and y is the distance between the O and the P. P is where we need to calculate the point whether it is a dark or dull, bright or dull, or maximum or min. Okay, so this is the information. And here, yes, look at this. This point means on the S2, one line is drawn over here, that is R2. The distance between S2 to this point, this is called path difference. This is extra travel distance. So once this extra travel distance is deleted, then both are okay. Both are will be parallel. So there we can get what kind of spot it is. So this path difference decides the matter that whether the spot is a bright or dull. Okay. Now, so with this information, we'll proceed to do some problems. Yeah, so yeah, this is information related to what the same concept, condition for maxima or bright fringe, means what are the formulae to get the bright fringe or bright fringe over here. So the path difference is calculating the condition for point P to be nth bright fringe, means at a point P maybe nth fringe is there, we don't know, that is which fringe is that from the center, okay. So let us take nth fringe, means first fringe, second fringe, third fringe, up to randomly we can select on the screen at a particular point that fringe may be nth fringe. So the path difference x is equal to, let us take that point just in the diagram. This point d sin theta is given, no? So d sin theta is the extra travel. So path difference, let us take x is equal to 2 pi. Actually, it is 2n times of lambda by 2. See, this is half. Now the phase difference is pi is equal to 2n pi. The formula pi is equal to 2n pi. The phase difference. Okay, right. So the distance of nth maximum is the formula where you can keep n value here. That is order, means number of fringe. For example, is a fringe number 1, then it will be 2 pi. Phase difference will be 2 pi. If fringe means fringe number is 2, then it is 4 pi. Like the values are changes here. So based on this, what is n here? N is the number of fringe. Now the distance of nth maxima from the central maxima is y is equal to, this is distance, y is equal to x d by d. X is what? Is the path difference. D is the distance between, okay, screen and the slit. Distance between the screen and the slit. Okay, and small d is the distance between the two slits. And this small d is very small compared with the wavelength of the incident light. So here is the matter. And for nth fringe, if you are calculating, this is the formula. So n is equal to 0, 1, 2, 3. Right now, condition for a minima or dark fringe. See, when on the screen we assumed randomly one point P over there. Maybe that P may be dark. Okay, so what will be the formula to getting a dark fringe chance? So the condition for point P to be nth dark fringe, then the path difference x is equal to this much, that is 2n minus 1 lambda by 2. 2n minus 1 lambda by 2. The phase difference is 2n minus 1 pi. Have you observed these two things? The path difference for bright one and what's that? Path difference for dark one. See? Okay. So now these are the formulae. Now the distance of nth minima from the central maxima is, so y is equal to, means y is means on the screen. Same formula, but where is in the place of path difference, we are placing this value, that is 2n minus 1 into lambda by 2. Okay, so where n is what? Okay, 1, 2, 3. Okay, and so on. So now moving to this fringe width. This is very, very, very important. What is fringe width? Fringe width means what? See, look at this diagram. So fringe width is nothing but on the screen, okay, on the screen, alternate bright and dark fringes are appeared that we have seen. Right? Now, yeah, look at this. Alternate bright and dark fringes are appeared on that. So on this, the fringe width means the gap between the two maxima or minima. How much gap will be there? Means at what intervals of the spaces this is forming. Right? So that is what is fringe width. That may be calculated for not only for maxima, we can calculate for minima also. Okay, so here is that fringe width means the distance between any two consecutive maxima or minima is called fringe width, indicates with the beta here. So fringe width, to calculate that we need to subtract the fringe width. So for example, we are calculating for bright, for example. See here, y means displacement, okay, of n plus 1 minus displacement of nth fringe. Right? So here are the formula, the two formulae. Okay, so subtract these two, you're getting same value, yd by d. Right? Fringe width is independent of order of fringe. See, because the fringe width is independent, what number of fringe is, we can subtract any two, means any consecutive fringes. If you subtract, then we'll get the same value. You get the same value. And it is same for bright and dark fringes. See, observe this also. For the dark fringe also, if you observe, okay, fringe width depends on the wavelength of the light used and the distance between the slits, the screen D, and the distance between the slits. Okay, here the terms are, means there's a fringe width that depends on lambda wavelength, okay, and distance between the screen and the slit, and also distance between the two slits. So this is the beta value, that is fringe width. Okay, so if you subtract the same for the dark also, you'll get the same value. Okay, now we'll proceed to solve some problems. So here a source emitted emitted a light of wavelength 480 nanometers. I'm repeating, the source emitting a light of wavelengths 480 nanometers and 600 nanometers is used in a double slit interference experiment. The separation between the slits is is 0.25 millimeters, and the interference is observed on the screen placed at 150 centimeters from the slits. Find the linear separation between the first maximum next to the center maximum corresponding to the two wavelengths. So what is asking? Find the linear separation between the first maximum corresponding to the two wavelengths. I hope you understood. The two sources are a source emitting two wavelengths, because it's a double. Okay, two sources are given, 480 and 600 nanometers wavelength. It is giving double slit interference experiment. So the separation between the two slits are given, small d value is, and these two are the lambda values, and the interference is observed in the screen placed at 150 centimeters, that is capital D value is, right, is asking what is the linear separation between the first maximum and corresponding to the wavelength. Right. So observe this. What information is given? We know that the first maximum means nothing but when there is no path difference is there, exactly both the rays which are coming out from the orifice, from the slits, incidenting on the screen, both are combining at a particular point. That is what is a first maximum. Okay, no, that is what central maximum. Okay, next maximum means from the center, either sides of those two fringes are next first maximum. Okay, so here we know that the first maximum that is next to the central maximum occurs at y is equal to d lambda by t. The whole information is given in the problem that lambda 1 is 480 nanometers and lambda 2 is the 600 nanometers. Capital D value is given, 150 centimeters is given, converting that into meters, and the small d value is given in nanometers. So it is 0.25 into 10 power minus 3 meters. Right. So we have a formula here. What is that? Y is equal to d lambda by t. So substituting all the values here, 480, yes, nanometers. No, it's millimeters in millimeter. Okay, so substituting all the values here, then we are getting what, 2.88 millimeters. Okay, and similarly the lambda 2 is also getting the value 3.6 millimeters. So the separation between these two bright fringes is given by, means due to first wavelength we are getting the displacement, means on the screen, okay, due to this one 480 angstroms or 480 nanometers, okay, we are getting the image on the screen at 2.88 millimeters from the center, and similarly due to 600 nanometers on the screen we are getting the spot, that is 3.6 millimeters from the center. Now, so the separation between these two bright fringes is given by. So what is asking on the screen? On the screen for these two wavelengths, we are getting some pattern. Then for these two wavelengths, what will be the distance between them? So at what separation? Both the fringes that we can see. So the separation between these two bright fringes is given by y2 minus y1, that is equal to, okay, so subtract these two, you're getting 0.72 millimeters. So I hope you understood the problem what is asking. So here two wavelengths are given. Because of the two wavelength, interference is occurred, and we have seen the interference pattern on the screen, and from the center maximum, okay, so these two are forming on the screen at different distances, y1 and y2. Then that gap they're asking, that is the distance between the separation between these two bright spots, fringes. Okay, so that's what this is. Here is the next problem. The separation between the consecutive dark fringes in a Young's double slit experiment is 1 millimeter. Slit experiment is separation between the consecutive dark fringes. Okay, right, means what value it is? Beta value is here. Okay, so consecutive dark fringes both are separated with some distance. Beta value is given 1. Now the screen is placed at a distance of 2.5 meters. Screen is placed, means capital D value is given, okay, 2.5 meters from the slits, and the separation between the slits is 1 m. So small d value is given 1. Now asking to calculate the wavelength of light used for the experiment. Okay, so I hope it's easy. So all the values are given in meters only. Yeah, all values are given in, here is millimeter, 10, yeah, 1 millimeter. Okay, so conversion is given. Beta is equal to 1 mm. Beta is equal to 1 mm, so 10 power minus meter, and 2.5 is given meters, and small d value is given 1 mm, so this is 10 power minus. So what is the formula we have? Lambda is equal to, no. The y1 is equal to, what is the formula? D lambda by d. Yes, sir. We have the formula y is equal to d lambda by d. So 2.5. See, y1 value is here, y value. Okay, right? So substitute the values over here, then you can get the lambda is equal to. Okay, so 1 by 2.5, 1 by 2.5 lambda. Take out the lambda here. So this will come to set. So 10 power minus 6. So is equal to, yeah. So 1 by 2.5 is 4 into 10 power minus 7. So 400 nanometers. This is the wavelength of okay, incident light ray we use in this experiment. Right? Now we'll move to the next problem. The electromagnetic radiation of frequency n, wavelength lambda, traveling with the velocity v in air, enters a glass slab of refractive index mu. The frequency, wavelength, and the velocity of light in the glass slab will be respectively. See, observe the options here. Relations are given. Right? See, n is nothing but frequency, lambda is wavelength, and v by mu is the relation for what is refractive index. What is refractive index? Refractive index is what is the it is the property of a medium that gives the information about how dense the medium is. What is the medium here? Glass slab is the medium. So glass slab has certain refractive index mu, and when the light ray velocity is there, no, when light ray is incidenting inside the glass slab, then there will be change in velocity. So that is the relation is given in terms of a refractive index. The four options. What is the situation here? While just the ray is moving in the glass slab will be, what happens? What will be the relations will be here? Three relations are given: frequency separate, wavelength separate, velocity and refractive index separate. See, yeah, the relations are given. Now we'll see here, frequency is given, wavelength is given, velocity in the air is v, and refractive index of glass slab is v. So what would be the relation? And see the options over here, right? Look at this. Frequency remains constant because when it's moving from one medium to another medium, the number of oscillations of that light wave particle within 1 second will not be changed, remains constant. So the four options, n should be same. They should not be 2n or n by 2, not like that. Now when it changes the medium, okay, when it changes medium, so medium has some refractive index, and refractive index is what is the ratio of wavelengths in vacuum, because refractive index is nothing but what? Change in velocity. Okay, velocity in air to the velocity of a medium. So this change is given in terms of wavelength. Okay, and similarly, refractive index is also ratio of velocities in vacuum and in the given medium. So the options are similar like this. Look at this. There is no question of 2 lambda. 2 lambda is not possible. Means while it is refracting, maybe lambda decreases, but here is a double. So this option is wrong. And here velocity with respect to changes while it is entering into the slab, means other medium. So velocity in the second option remains same. So this option is also wrong. And coming to the third option, of course, the velocity, yeah, frequency, look at this frequency here. In this case, the frequency is divided by mu, refractive index. So the frequency will never change. The frequency, medium changes, no, it will remains constant. But the frequency is changing here. So this option is also wrong. And what would be the chances here? B option here, the frequencies remain constant. And look at this, for both velocity and wavelength, both velocity and wavelength are divided with the refractive index. Yes, so these two are function of what? Refractive indices. So B option may be correct. Right? Now we'll move to the next problem, that in Young's double slit experiment, the distance between the slits and the screen is double. The slit and the screen is double. Then the screen is double. Yeah, in the Young's double slit experiment, the distance between the slits and the screen is double. Then the separation between the slits is reduced to half. The separation between the slits is reduced to half. Now, as a result, the fringe width formula is this. What is asking? Distance between the slits means small d. No, wait. Distance between the slits and the screen is doubled, means capital D is doubled and the separation between the slits is reduced to half, means small d is divided to half. So small d will become d by 2, capital D will become 2d. Then what will be the fringe width they're asking? Okay, so options are given. Now look at this solution that here fringe width formula is given, beta is equal to lambda d by d, and where d is given the problem, where d is the distance between the slits and the small d is the distance between the slits, and capital D is the distance between the screen and the slits, and small d is the distance between the two slits here. And now if capital D is doubled and small d is reduced to half, then the fringe width becomes, so substitute all the values in this expression, then we can get, look at this, beta is equal to lambda is as it is, d just we wrote this as in a 2d, and small d is in a d by 2. Then what happens, so 2 come here, then lambda 4 lambda d by small d. So again you got lambda d by d here, similar to this, so lambda d by d. So the finally how much fringe width you are getting? 4 times. 4 times. If the slit width is half and the screen width is doubled, then the fringe width will be 4 times increase. Okay, right? So these many problems will be asked in exam, this type of problems. Okay, now we'll move to the next problem. Right. A linear aperture whose width is 0.02 centimeters. Linear aperture is 0.02 centimeters is placed immediately in front of the lens of the focal length 60 centimeters. The aperture is illuminated normally by a parallel beam of wavelength 5 into 10 power 5 minus 5 centimeters. Now the distance of the first dark band of the diffraction pattern from the center of the screen. He's asking diffraction. He's asking diffraction. So diffraction means what? Diffraction is when light ray is incidented, when the light ray is incidented on the edge of an obstacle or passes through a narrow orifice, then the light ray bends. This bending phenomena is called diffraction, right? So in this diffraction, the aperture means a small narrow gap. Aperture is that. Centimeter is given, that is 0.02 centimeters is placed immediately in front of the lens of the focal length. So to get the exact means again in this 2 types of diffractions are there, Fraunhofer diffraction and Fresnel's diffraction. So here one of them we are using lens to identify the clear pattern if the distance between the screen and the slit is very far, right? So focal length of means a lens here we are using focal length of 60 centimeters. And the aperture is illuminated normally by the parallel beam of wavelength. So what kind of light we are using here? 5 into 10 power minus 5 centimeters wavelength lambda we are using. And the distance of the first dark band of the diffraction pattern from the center of the screen is, see the comparison between this interference pattern, that is a double slit experiment, and the diffraction pattern is, in the interference concept on the pattern, if you observe, all the alternate bright dark fringes will be with the equally spaced. with almost the same intensity. But in the case of diffraction, on the pattern, the central one is maximum, and either sides of that maximum, the either dark or bright fringes, okay, decreasing intensity will be there. Intensity is not same for the diffraction pattern. So from the center, as distance increases, intensity of that pattern is decreases. Whereas in the case of interference, the pattern will be the same. Pattern will be the same. Means from the center, if you go away from the center, all the alternate bright fringes will be with the same brightness. Whereas in the diffraction, as the distance increases, the intensity is this. So what is asking? The distance of the first dark band of the diffraction pattern from the center of the screen is. From the center of the screen is. Yes. As per the information, A value is given, that is the aperture width 0.02 centimeters. So convert that into meters, so 2 into 10 power minus 4 meters. Lambda value is given, means what kind of wavelength we are using is 5 into 10 power minus 8 meters value is given. And a D value is what? The distance between the slit and the screen is 60 centimeters. Okay, that is 0.6 meters. Now look at this, the position of the first maximum. Position of the first maximum on the diffraction pattern. So formula is Y is equal to D lambda by D that we used in the interference. Now we are using its aperture, the same. That's what aperture. Okay, small a is a gap between the two edges. Right, so it's not a double slit, it's a single slit only. Okay, so that one slit if you are taking, then that slit edges. I told you, no, the light ray passes through a narrow orifice, narrow gap. So edges between that gap is A here. So D value is given in the problem, that is 60 centimeters, that is 0.6. Right, lambda value is given 5 into 10 power minus 7. And A value is given 0.2 centimeters. So converting that, it's a meters, 2 into 10 power minus 4 meters. And calculate this, you're getting okay. So 15 into 10 power minus 4 meters you're getting 0.5. Yeah, 15 into 10 power minus 4 meters you're getting. So it is nothing but 0.15 centimeters. So this is what is the from the center, the first dark fringe. First dark fringe appears from the central point, from the central maximum. Okay, from the center maximum of the diffraction pattern, the first dark maximum, first dark is appears at a distance from the center is 0.15 centimeters. Okay, now we'll move to the next problem. Yes. In a double slit experiment, two slits are 1 mm apart and the screen is placed 1 meter away. Observe the values are given, right? 1 mm is small t value, 1 m is capital T value, a monochromatic light of wavelength 500 nanometers, this lambda value is given. Then what will be the width of each slit for obtaining 10 maxima of double slit within the central maxima of single slit pattern? Okay, for the same experiment, the widths are, means what will be the widths of width? The width is asking, fringe width they are asking. For 10 maxima for double slit and single slit pattern. How much will be for the single slit pattern they are asking? Okay, so a monochromatic light is used. What will be the width of the each slit for obtaining 10 maxima of a double slit within the central maxima of single slit? Right? Look at this. The answer For a double slit experiment, see, for both of them, the fringe width formula is same one, right? The values are just converted over here, and the formula is this: fringe width beta is equal to dB, beta is equal to d lambda by d. So width of the central maxima in a single slit. Width of the central maxima in the single slit. Width is given. Central maxima. Okay. On the screen, the central one is, of course, the bright one, maximum one. Means bright one, maximum one. So whose value is always 2 lambda d by A. Now, this is for single slit. Now, as per the question, the width of the central maxima of single slit is equal to width of the 10 maxima of double slit pattern. This is the problem. Okay. So, this one is for double slit, and this value is for single slit. How many double slits are there? 10 times. Now, how many single slits are there? One central maxima. Okay, one central maxima. And when these two are equated, so this is the question. Then what you are getting? What is the aperture value or distance between the two narrow slits? A value. Yes, that's what is asking. Look at the problem here. What will be the width of each slit for obtaining 10 maxima of double slit within the central maxima of a single slit? Okay, so equating these two, that is for single slit, 2 lambda d by A is equal to 10 times of fringe width, that is 10 into lambda d by d, that is equal to lambda d gets cancelled. You know, which you're getting, this will come to say 2d by 10 is remain. So if taking A out, you're getting 2d by 10. So 2. D value is given. D is how much is small d is how much? 1 into 10 power minus 3 is there. Okay, right. So you are getting 0.2 into 10 power minus 3 meters. That is 0.2 millimeters. So this is what is the aperture value or slit width. Means both the slits, width of the each slit. Okay, slit width they're asking. So this is the 0.2 mm is the answer. Now we'll move to the next problem. Here is a problem that at the first maximum, at the first minimum, adjacent to the central maximum. See, this is related to diffraction pattern. I told you diffraction pattern, always the central one is bright one, and rest all means on the either sides of the pattern, either sides of the central maximum pattern. Okay, all the fringes are decreasing one. Intensities are decreases. So this will be first minimum. Maxima and minima will be appeared on that. First minimum means from the center is a bright, that is maxima, and immediately after that will be what? Minimum. That is first minimum. Okay, on the single slit diffraction pattern, the phase difference between the Huygen's wavelet from the edge of the slit and the wavelet from the midpoint of the slit is. Okay, so the phase difference that we know, both are coming out from the slits, the edges. With the help of that, we have drawn Huygen's wavelet. We already studied how to draw a wavelet over there. Okay, so wavelet. Then from the edge of the slit and wavelet from the midpoint of the slit. Yes, because between the two edges of the slit, the number of bunch of particles are entering into the slit, light particles. The light is entering into the slit. Now, as per the Huygen's principle, what you studied, whenever a light ray is started moving, okay, source from the source. So all the particles in the medium starting getting uh, vibrating, the disturbance is started. So they create the secondary waves. And the secondary wavelets again acts as a primary source to create one more secondary wave. So drawing the all the tangents over there. So this is what wavelets that we studied in the Huygen's wavelet form. So the slit is given. The slit is two edges, having two edges, and exactly one more means exactly the center of that the slit. One more point, one more wavelet is also created. That is what at the midpoint. Wavelet from the midpoint of the slit. Then for these two cases, what they're asking at the first minimum adjacent to the central maxima of the single slit diffraction pattern, the phase difference between the Huygens wavelet from the edge of the slit and the wavelet from the midpoint of the slit is okay. Right. So now we'll see the answer for this is the diagram that now I'm trying to explain this. See, A, B, capital A, capital B is the total slit gap. That is A here, right? Actually, the rays starts meet from A to B. Both will move from A and B instance on the screen. But what in the problem is given, the another wavelet means at a point C at the midpoint of the total, the slit that is A by 2 at a distance A by 2. Here the point is making wavelet. Now this delta X is the path difference. Okay, delta X is the path difference for these two waves which are started from A and C. So this is the situation. So for this case, what they're asking, what is the path difference, sorry, phase difference they're asking. Yes, sir. What the value they're asking? The phase difference between, they're asking phase difference. Okay, right. So in the figure, look at this. A and B represents the edges of the slit. Represents the edges of the slit. Okay, and AB is the width A, small a, that is aperture value, and C is represents the midpoint of the slit for the first minimum, and that value is nothing but this value. Okay, this value. From the first minimum, let us take this point, both are incidenting at a point P here on the screen. Then this you want to be minimum. Okay, so for a minimum, what is the condition? Path difference is equal to integral multiple of lambda. It should be equal to lambda here for getting minimum. A sine theta is the path difference. A sine theta is the path difference is equal to lambda. So where lambda is the wavelength of incident light ray. And the path difference between the wavelets from A to C is, we have in a formula, delta X is equal to path difference, that is A by 2 sine theta, A by 2 sine theta, this is path difference, okay, that is equal to, okay, 1 by 2, means we have a relation here, just we are rewriting this as this, so A sine theta into 1 by 2, that is equal to how much difference is? Lambda by 2, okay, so because the relation is A sine theta is equal to lambda. Okay, so this whole thing, because A sine theta is A sine theta by 2. So this becomes lambda. What is this? Path difference. So corresponding phase difference, just we got path difference also. That is our delta X is equal to lambda by 2. Now substitute in our regular formula that delta pi, that is phase difference, is equal to 2 pi by lambda into delta X. Okay, so 2 pi by lambda into what is delta X you are getting here? Lambda. So 2 gets cancelled, lambda gets cancelled, and you are getting pi value. So what is the phase difference for these two getting a minimum value, minimum fringe on the pattern is pi radians. Okay, if the path phase difference is pi, then you are getting minimum. You are getting minimum fringe on the screen. Now we'll have one more problem now. A parallel beam of monochromatic light of wavelength, beam of wavelength 5000 angstroms is incidented normally on the single narrow slit of width 0.001 millimeters. Okay, 0.00 millimeters, right? So the light is focused by a convex lens on the screen placed on the in a focal plane. Now the first minimum will be formed for the angle of diffraction is equal to. Okay, I told you know the diffraction is of two types, right? In one of them we are using lens here, focal length is given. Focal length is given. Yeah, just focused. Light ray is focused on using the convex lens on the screen. Okay, placed in the focal plane, right? So the first minimum will be first minimum. Okay, so the formula is, you know, I told you know the path difference. Okay, a sin theta is equal to n lambda. A sin theta is equal to n lambda, and for which one is asking single parallel. One second. Right. So we'll conclude with this problem. Okay, the time is going up here. The light is focused by the convex lens on the focal plane. The first minimum will be formed. First minimum. So on the screen, at what angle the first minimum spot will be appeared with the diffraction. Okay, means from the center. Now for the first minimum, the path difference is what? A sin theta is equal to n lambda. N is equal to 1 here. That is what? First minimum. They are asking for first minimum. So 1 lambda. Therefore, sin theta is equal to lambda by a. So lambda value is given over here 5000 angstroms. That is 5000 10 power minus 10, and this one is given in millimeters. So into 10 power minus 3. So you are getting 0.5, or simply theta is equal to 0.5 is equal to 1 by 2. Right. So sin theta is equal to 0.5. So theta is equal to 30 degrees. So the image means the pattern will be what? With the central spot, the first first maximum minimum. Yeah, minima is making angle 30 degrees with the center line. So this is where this is yeah. We'll conclude with this problem. Okay. So we'll continue the next class with a few more problems. Thank you very much. Keep practicing. Okay. Thank you very much.